Hey, Twelves. So today's video will be on subtopic 3.8, amides. It'll be a short one today, so there's not a whole heap of content that you have to know for this particular section. Now, amides are similar to esters. You've got a condensation reaction that liberates water molecules, but instead of joining carboxylic acids to alcohols, we're going to be joining carboxylic acids to amines instead. Now, you've seen here, we have our two molecules that we're going to be joining together, one being our carboxylic acid and one being our amine. Now, what I'm going to do here is I'm going to name this one here live. So just a reminder, we have 1, 2, 3, 4, 5 carbons in our carboxylic acid. So this will be pentanoic acid. Now, when we join our pentanoic acid with our propylamine, now just a quick little note here, as you can see, that you do not need to be able to name these amines, just a reminder from the subtopic 3.6. But I'm giving you the name here. It's an amine and it's got a propyl group, 1, 2, 3 carbons sticking off of it, so propylamine. And we are going to make an amide from that, which means we're going to take our OH from our carboxylic acid, as we usually do when we make as we did from our esters. We'll join it and remove that. Along that, we'll remove a hydrogen from the amine, and we are going to liberate water and join them together in an amide bond. So this amide bond is our double bond C double bond O, and that carbon is attached to an NH group. So nitrogen more specifically, and it's similar to an ester, which has the C double bond O attached to the nitrogen. Now this bond here, the one between the carbon and the nitrogen, that's the one that will break when we hydrolyze this, which we'll talk about soon. Okay. Actually no. I changed my mind. So I'm not going to just redo the same equation again and split it up. What I've done is I've used an arrow that goes back and forth to show that if we add water to this N-propyl pentanamide, it'll break at the spot here, and then we'll end up making our starting substances. So if we take our, so instead of just joining them together in one bond, if we take a diol, so here I've got a chance to name this one here. So we have 1, 2, 3, 4, 5 carbons. So this will be pentane dioic acid. So pentane dioic acid tells us we've got our 5 carbons, and we've got our, instead of oic acid, it's got 2 of those groups. So we've got our carboxylic acids on both ends, and we're going to combine it with our 1,3-diaminopropane. So 1, 2, 3 methyl prop. So it's a propane with amino groups on both ends, and because those amino groups could be in the middle, we pretty much say 1,3-diamino. So you have to say the location of those ones as well. Don't have to name it, so don't stress out too much about that. Now, when we join them together, we are going to make a polymer. Now, because we have carboxylic acid groups on both ends and we have amines on both ends, when you join them together once, you then still have these functional groups on the ends that can be reacted with, and so the molecule will stretch out, and we end up with this being our unit that we stretch out into a polymer. So you have our pentane part here, which are 1, 2, 3, 4, 5 carbons. Then we have our 1, 2, 3 carbons in the next section in between the amino groups. Either way, this makes our polyamide, so which is essentially a polymer. Now, this last bit is going into a bit more specifics about breaking up these amides. So when we hydrolyze them, which means we add the water back in to undo the condensation reaction, we are breaking this bond along here. But if we do this in acidic conditions, we are going to liberate a carboxylic acid. So methyl prop, so propanoic acid, along with ethyl and amine. So this one here, again, you don't have to be able to name this, but you do have to know that if the amine will act as a base when in an acidic condition, which will add an extra proton to it, the extra hydrogen, and it will end up positively charged. So it's the reason why this can happen is because the lone pair on the nitrogen that's normally there, it can act as a base and accept a proton from the acidic environment. Now instead, if this reaction is done in basic conditions, so we take a different molecule, I gave this a different, so I used a different one just for fun, we're going to break this bond again, but instead of making our carboxylic acid and our ethylaminium, so our charged version of our amine, we'll end up with our ethylamine, which is uncharged. Actually, 1, 2, 3, yep, no. This is actually not ethyl, yeah, I don't know why I call it ethylamine. It's actually butylamine. Oops, just dropped the pen. Cool, let's fix that up right now while we're here. Yeah, butylamine. So we have our 3 carbons, not our 2. Now, I've given myself a chance to name this carboxylate ion. You do not have to be able to do this, so I'm just doing it, for fun. So because we have our 1, 2, 3, 4 carbons, so we have our meth, eth, prop, bute. So it's going to be bute something. So because it is a what do you call it, a carboxylate and not a carboxylic acid, so we call it butanoate ion. So it's an O8 instead of an oic acid. So butanoate, often they have different names, so I think it's like butyric or something, but it doesn't really matter. This is the systematic name. The butanoic acid is instead a butanoate ion. So that's for a simple, just a simple single bond that we're breaking. Now, if we have polyamides, so we have those polyamides that we made just up here, when we break them, we're going to be breaking these amide bonds, and they can be done in different conditions as well. If it's done in an acidic condition, you will make our dioic acid, so our carboxylic acids on each end, as well as our charged amine. Essentially the same as what we talked about up here. Now, if we do it in a basic condition instead, we're going to strip away and make it a dicarboxylate ion, and our amine that we would have started with normally. So pretty much no matter what, there's going to be a difference in one of the two depending on the conditions. Either you take our carboxylic acid in acidic conditions and you add protons to the amine, or if it's in basic, you strip away the protons from the carboxylic acids to make the carboxylate ion and leave the amines or the diamine uncharged. And that's pretty much it for this section. So I hope that helped.